Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fakhr Lodi, and this is our 23rd lecture of Formal Methods for Software Engineering. In the previous lectures, we have been discussing algebraic specifications. Algebraic specifications क्या चीज़ हैं? As we discussed previously in the last lectures, we use algebraic specifications to specify abstract data types, specify the behavior of abstract data types. And they are used for the specification of interfaces as well. We shall talk about that a little later. In an algebraic specification, as we discussed last time, we have a number of things. There are 4 sections of an algebraic specification, typically, and those 4 sections are, the first one is the introduction, where we specify the name of the sort for which we are giving the specification. And then, there we also specify what are the different other specifications that we are using inside, and so on and so forth. So that is one part. The second part is informal specifications. So we provide informal specifications with the algebraic specifications. So the operations that are supported by this abstract data type, we give an informal specification or the definition of what these operations are supposed to do. Then we have the sort of the header, what is known as the signature part, where we declare sort of the operations that are supported by this abstract data type. Here in this section, that is the signature part, we specify, we just give the names of the operations along with the parameters, that is the type of the parameters and the number of parameters, along with the return value that we get from this data type or this operation. And finally, in the last part where we have the axioms, this is where we define the semantics of our operations. So what we do is we specify the behavior of the operations by providing the specification of our inspector operations in terms of the constructor operations. Inspector operations are those operations which gives you a value back without changing the state of the abstract data type. And the constructor are those where we change or modify the state of the object that we are working with. So in that includes our constructors that create the object and other things that modify the state of that object. So this is the general structure of an algebraic specification. And we discussed it in detail in the last couple of lectures. In the last lectures, what we did was we saw how to write axioms for these algebraic specifications. So there were a couple of things that we did. The first rule of thumb that we used was write the axioms for our inspectors in terms of the constructors. So that was the first rule of thumb. And we did that, and we wrote a simple specification with the help of that rule. Then we saw that in some cases, it is not very easy, it is not sometimes possible to define an inspector in terms of all the constructors. There may be some constructor for which this definition is not very easy or not possible. So for that case, what we did was we said, okay, we will take that constructor and then we will define that constructor in terms of other constructors that are available, and hence we will complete the specification just like that. In the specification, we saw that we could use recursion to specify the specification. And the last time what we did was we were discussing the list sort, or the algebraic specification for a sort list. And there we saw that we used recursive definition of different functions. There were a couple of functions for which the recursive definition was straightforward. That is, example of that is the length function in the list sort that we saw last time. When we were defining the list and the length of the list, we said that when we add one element to the list, the length of the new list is equal to the length of the old list plus 1. So that is what the recursive definition was, length in terms of length. Then we also saw the cons and tail that we did last time. And if you remember, what we did was we specified tail in terms of cons, and then on the right hand side of the equation we had cons in terms of tail. So there is the indirect recursion that we had in that particular case. So once again, recursion, like I mentioned last time also, it's a very powerful tool, and it's very useful and handy when we write these kind of specifications. A lot of times what happens is that we have the constructors and we have the inspectors, and when we try to write the axioms, it is not very easy to write the axioms with the given set of constructors. So what we do in that particular case is, in order to simplify our specification, we may, or we are allowed in this mechanism to define some intermediate kind of functions that may not be available for external use. It is just like your private functions in a class. So if you have some private methods in a class, those private methods can be used by your public methods, but they are not available to be used from outside this class. And the main purpose of defining those private methods is to simplify the implementation. So maybe you have some task that you need to perform. So what you do is you make a private method, and that private method is called by your public method, or maybe called from different public methods, and it simplifies the implementation of the public method. The same is basically what we are going to do here. We have a set of operations defined for a particular sort, but if we see that it is difficult to achieve our purpose or write the axioms or specify the behavior, because sometimes it becomes a little bit too complex and complicated, then we may define some additional constructors or those kind of methods, and then we can use those methods to write the specification for the base or the original method that we had. So this is another way of writing axioms for your algebraic specifications. So the first example that we are going to see today uses that concept. In this example, what we are going to do is we are going to write the algebraic specification for a binary search tree. If you remember, a binary search tree is a search structure, is a binary tree and a search structure with certain properties. The properties are that, a binary search tree, we have some data in the root, and actually data is stored in all the nodes in that tree, with the property that the data on the left, or all the data elements on the left of the root, they are supposed to be less than the data in the root, and the data on the right is greater than or equal to the data in the root. If there is duplication, then we have the equal or equality there. Also, equality could be on the left or on the right, depending upon how do you define it. But typically, we write that if it is greater than or equal, it should be on the right. And then the left subtree and the right subtree, both these subtrees, they are also binary search trees. So this is the recursive definition. So when we search for an element in a binary search tree, we do, we go to the root, we look at the data, and we compare the data with the key that we are searching for. And if the key is smaller than the data in the root, then we go to the left. If the key is larger, then we go to the right, and we keep on doing this thing until we find the key, or we reach the end of the tree and there is nothing to be looked at. That is, we reach a node from where you cannot go, for example, to the left if you were looking for something which was smaller than the data in that particular node, but the left subtree in that particular case of that node was empty. So this is, once again, remember, this is what the binary search tree is. Now we have to write the algebraic specification for the binary search tree. And the operations supported for the binary search tree are, once again, the same kind of operations. I'm going to give you the formal signature for those operations, but those operations, obviously, we want to create a binary search tree, which would create an empty binary search tree. Then we would want to add, we would want to search, and so on and so forth. So those operations need to be supported by that binary search tree. So let us first look at the signature part of the binary search tree, and then once we have that, we will write down the specifications of that binary search tree, and then we shall see why and how can we use some auxiliary methods and define those auxiliary methods, and then define our axioms in terms of those auxiliary methods. So let us look at this slide. So the methods that we have that are supported by this binary search tree are create, which creates an empty tree; add, it takes a binary tree and an element, and it adds a node to the binary tree using the usual ordering principle. Then we have the left of binary search tree, which returns the left subtree of the top of the tree. Then we have the data binary search tree, which returns the value of the data element at the top of the tree. Then we have the right of binary search tree, which gives us the right subtree. Then we have the function isEmpty, which tells us whether the binary search tree is empty or not. And then we have the search operation. We have this contains binary tree element, which returns true if the tree contains the given element, otherwise it returns false. So this is the basic signature of the binary search tree. So we have the create, which creates a binary search tree; add, left, data, right, is empty, and contains. In this particular example, if you try to write the specification for this binary search tree, you will see that it is not very easy to do that. So what we do is we have this additional function, which is an additional constructor, and name of this constructor is build. This build constructor, it takes three elements or three arguments. The first argument is a binary search tree, the second argument is an element, and the third argument is once again a binary search tree, and it returns a binary search tree. The basic purpose of this build is that given two binary search trees, that is, if I have the left subtree of a binary search tree and a right subtree of a binary search tree. It joins these two together, and then I give an element that is greater than all the elements in the left subtree and smaller than all the elements in the right subtree. So I am building this subtree by joining, by creating a new node with this element, and the first argument is the left subtree of that new tree, and the right argument is the right subtree of this new tree. So this is what my build operation is. So having done that, I have this new constructor that I did not have initially. And this new constructor, although in the specification it does not say that it is sort of a private member that is not supposed to be used from outside, but this is what we are going to do, because in the original list we did not have this method, and that is not to be exported for external use. Now we write the axioms for this binary search tree. In this case, we have a number of constructors. We have this constructor create, which creates a binary search tree. We have this constructor add, which modifies this binary search tree and gives us a new binary search tree. We have the left, which once again creates or modifies a binary search tree by giving us the left subtree of the binary search tree. We have the right, which gives us a right subtree of the binary search tree. And we have this new constructor build, which given the left subtree and the right subtree and the data in the root node, that would create this new binary search tree by joining the left subtree and the right subtree and adding this new node as the root of the tree. So we have these number of constructors here: create, add, left, right, and build. Actually, once again, if you try to write specifications using these constructors, specifications for the inspectors, and the inspectors are data, which gives you the element in the root node of the binary search tree, is empty, which tells you whether the tree is empty or not, and contains, which tells you whether the tree contains an element or not. So if you look at this specification, if you try to write the axioms for the inspectors in terms of all those constructors that we just saw, once again you will see that it is not going to be easy to write axioms for all of them. You try that, I strongly encourage you to try that and see if you can do that. But it is not going to be easy. It is going to be a tricky business. So first of all, like I said, that if you did not have the build there, it would not have been easy at all. But even with this new constructor build, it is not going to be easy. So once again, if you do that and if you try to write axioms, you will see that there are number of constructors that actually you will be stuck there when you try to write some axioms for inspectors in terms of those constructors. And those constructors that you will have, they will be the add constructor, the left constructor, and the right constructor. And once again, what we will have to do it, we will have to fall back onto the same mechanism, that is, we take them as inspectors, or they are not really inspectors, but then we will write the inspectors, we will write the axioms for these constructors in terms of the other constructors that we have, and the other constructors that we had, they are the create and the build. So we have just two constructors left, create and build, and then we shall be using those to write the axiom for the rest of the operations that are defined here. So how do we do that? Let's once again go back to the slide and then see what to do with those axioms. So here we have the first one. We have add, create, E. So, we are adding the first element in an empty tree. So what happens, when you create this empty tree, when you add the first element into the empty tree, you will create a binary search tree with only one element there. So the one element will have this data E, and the left subtree will be empty, and the right subtree will be empty. So we can write this thing, that is add create E is equal to build create comma E comma create. That is, the left subtree is empty and the right subtree is empty, and we have just one node. Now let us look at the second case when it is not an empty tree. So we have add B comma E is equal to, if E is less than data B, then add left of B comma E, else add right of B comma E. So what does that mean? This is once again a very important and interesting point that you need to understand and note here. What we are saying here is that when we add an element into a non-empty tree, if it is less than the data in the root, then we add in the left subtree, and otherwise we add in the right subtree. So बिल्कुल वही मैकेनिज्म है जो बाइनरी सर्च ट्री में जो बेसिक डेफिनेशन है कि अगर इट इज स्मॉलर you go to the left, if it is larger you go to the right, and you build your tree just like that. So what will happen is, let us try to understand how actually, what is the mechanism, what is going on here. Let us assume that we have this tree here. Let us assume that this is a binary search tree. As you can see that it fulfills the properties of a binary search tree. Now we want to add this data with the information, the 7 there. So I want to add 7 there. So my axiom says, I want to add B. This is the tree and the element, and the axiom says that if E is less than data in B, then I add in the left of B the element that I need to add, else I add to the right. So this is the axiom. And remember that there is also another axiom which says when I add a node in an empty tree, what I need to do is, this is basically, I say build a tree using the left subtree as an empty tree, the root with this data E, and the right subtree as an empty tree. So these are the two axioms that I'm going to use here. So I need to add this data with this 7 there. So my tree is a tree which is not empty. This is the tree that I have. So I go here and I compare it with the data at the root node. And since this E is 7, so I will go to the left. When I go to the left, it says add in the left subtree, add in this left subtree that I have. Then I compare it here. Once again, I compare, this is 7, and the data at B is 5. So it says add to the right subtree. So I go to the right. When I come here, once again, I compare it, the 7 with this data here, since it is to be added on the left. So it says add to the left of B. So I will be adding this thing onto the left of B. But this is empty. Since this is empty, this is the axiom that now comes into picture. This is the axiom that now comes into play. So what I do is, it says build. And how does it build? It says here is a new node that I add. This new node will have the data that I supply, and the left will be empty and the right will be empty. And then I'm done. Because after this, there is no recursive call of this add function. So here you saw कि ये build के साथ किस तरीके से हमने एक बिल्कुल लीफ लेवल पे पहुंच के हम एक नया नोड क्रिएट करते हैं जिसके लेफ्ट एंड राइट they are empty. It is a new leaf in our system that we have. So whenever we hit a node which is an empty, that is either the left or the right is empty, the second axiom will come into play. And the second axiom says, okay, if the tree is empty, now you have gone to the left subtree and that left subtree was empty. When you build, that means you create a tree, create a node for which the left and right, both of these, they are empty, and then you plug that with the previous one, and that is what you get. So ये build की मदद से आपने देखा कि कितनी आसानी से हमने ये चीज़ कर ली, इसको डिफाइन कर लिया. अगर ये build का मेथड ना होता तो शायद इतनी आसानी से ये काम ना हो पाता. ये build को हम और जगहों पे भी इस्तेमाल करेंगे और देखेंगे कि how does it help us. So the other operations are the left of create, we define it to be create. So left of an empty tree is an empty tree, there is nothing there. The same is true for right of create is create, and the data for create is undefined. So here you saw, once again, I am avoiding specification of the error conditions. तो उस केस में हमने ये कहा कि left of an empty tree is an empty tree. शायद in many cases you would want to raise an error or an exception condition कि अगर आप null pointer आपको hit कर जाए और उसके आप left पे जाना चाहें, you are not supposed to go to the left and so on and so forth. But यहाँ पर मैं अभी एरर कंडीशंस की बात नहीं कर रहा, ज़रा मैं उसको अवॉइड करना चाह रहा हूँ. वी विल बी looking at the specifications where we specify the error conditions also. So otherwise there is nothing special about this these three axioms. It is straightforward thing, that is left of create is create, right of create is create, and the data of create is undefined. When you have a null pointer, you cannot take the data out of it. Once again, we are not specifying an error condition in this particular case. So let us look at the rest of the specification. Then we have the left of build LDR, where L is the left subtree, D is the data, and R is the right subtree. So left of build is going to be L, and right of build LDR is going to be R, and the data of build LDR is equal to D. Once again, this is a straightforward specification. Nothing very special about it. कि आपके तीन कंपोनेंट्स हैं एल डी आर, जब जिससे आप अगर ट्री को बिल्ड कर रहे हैं. सो इफ यू टेक द लेफ्ट ऑफ दिस ट्री विच हैज बीन बिल्ट with the help of this function, the left of this would be L, the right of this would be R, and the data of this would be D. So once again, कोई शायद इसमें मुश्किल नहीं है, बड़ी स्ट्रेट फॉरवर्ड सी बात है, बिकॉज यही L और D और R का मतलब ये है कि लेफ्ट सब ट्री, data, and the right subtree. Now we have then is empty create is equal to true, is empty build LDR is equal to false. Once again, there is nothing very complicated about it. Now we have a more interesting specification or axioms. First one is obviously very simple, contains create E. Since it is an empty tree, so it does not contain anything, so E is not there, so hence the answer is false. Now the second axiom is interesting. We write contains build LDR comma E. So we are building a tree with this build function, and we have these three parameters L, D, and R, and we want to check whether this has the element E in it or not. So the answer is very simple. If E is equal to D, then it is true. Otherwise, if E is less than D, then we will check whether it is contained in the left subtree. So we say contains L comma E. Otherwise, we check whether it is contained in the right subtree. So we say contains R comma E. So once again, it is a recursive definition in this particular case. So once again, आपने देखा कि ये किस तरीके से हमने अपनी स्पेसिफिकेशंस लिखी, एंड इस स्पेसिफिकेशन में कोई नई बात नहीं थी, स्वाय इसके कि हमने एक ऑक्सिलरी फंक्शन यूज किया जो कि अदरवाइज हमारे पास अवेलेबल नहीं था, जो इट इज़ नॉट अवेलेबल फॉर एन एक्सटर्नल यूज, इट इज़ नॉट पार्ट ऑफ द ADT specification. So we defined a new function to simplify the specifications. And once we have that new function, the specification was straightforward. If we did not have that function, आप इसको ट्राई कीजिए, और अगर आप कोशिश करते तो you would have found out the specification is not going to be that easy. So ये हमारी ये इस एग्जाम्पल में खास बात थी. So next we have is, if we have already written a specification, we have seen that we can import other specifications and use those specifications in other specifications. That is one thing. जिस तरीके से हमने integer को use किया था या boolean को use किया. But in many cases, what happens is that we have written a specification, and now I want to sort of enrich this specification. कुछ उसमें नई चीजें ऐड करना चाहता हूं. This would be the case अगर मैं फॉर एग्जाम्पल अपनी क्लास में इनहेरिट कर रहा हूं, मैंने एक क्लास बनाई है बेस क्लास, उससे मैं डिराइव्ड क्लास इनहेरिट करता हूं, So what happens is I inherit everything from the base class, and in the derived class or the child class that now I get, I have everything that was already there, and I may add a few more things. So this is the kind of mechanism that we want to have in our specifications also, so that we don't have to rewrite that specification again that we have done when we are enriching, or when we are I don't want to use the word inherit, because that is not the terminology used in algebraic specifications, but that is what it is supposed to be. It is very, very similar to that part. We shall see this thing with the help of a very simple example. In this particular example, we have the specification of a coord. This is a coordinate. So the name of the sort is coord. It imports integer and boolean, so it uses those. So this is basically a Cartesian coordinate where we have two components, x and y components of a Cartesian coordinate, which can be used to define a point and things like that. So we have the create. Create method takes two integers and it gives us a coordinate. I can apply this function x on a coordinate. So I say, give me the x component of the coordinate. It gives me an integer value back. And I say, give me the y component of the coordinate, and it gives me the y component back, which once again is an integer. And I can equate two coordinates, and if they are equal, it will give me a Boolean result, true or false. So once again, a very simple specification, nothing very complicated about it, but we shall use this specification. First of all, we need to write the axioms for this specification, and then we shall use this specification to create a new specification, and that specification will actually use whatever we have already given here. So let us look at the axioms first. So if you can see this thing, there is one constructor and there are three inspectors. So the constructor is create, and the inspectors are x, y, and equal. So we will write axioms for these three inspectors in terms of this constructor create. So we have x create two arguments. Let's call them a and b. So when we create a coordinate, it creates this coordinate by taking these two arguments, and the first one is the x coordinate and the second one is the y coordinate. So if I want to get the x coordinate of this whole quad, the answer is going to be a. Similarly, y of create is going to be b, and equal once again is not going to be difficult. We create two quads and we say it is a equal c and b equal d. So in this particular, what happens is very simple. There is no complication about this specification. जो एक छोटी सी चीज़ जो आपने शायद नोट की हो वो ये है कि इक्वल के केस में मैंने क्या लिखा है, आई हैव रिटन अ बूलियन एक्सप्रेशन A equal to C and B equal to D. And the result of this Boolean expression is either true or false. I could have written if A equal to B and A equal to C and B equal to D, then true, else false. But this Boolean expression basically means the same thing. So I did not have to write if then else in this particular case. So very simple specification. This specification we are going to use in the first example. What we are going to do is we are going to use this quad just like we have used the integer and Boolean, but in this particular case it is going to be a little bit more complicated and involved as compared to integer and Boolean that we had earlier on. So the idea really is we write down the specifications and then we use these specifications to build bigger and more complex specifications. So this is the first example. What we are going to do is we are going to write the specification for a sort called cursor using this quad. How do we do that? Let us go back and look at the slide. So here is the sort cursor. This is cursor is a representation of a screen position. Defined operations are create, which associates an icon with the cursor at a screen position. Position, which returns the current coordinate of the cursor. Translate, which moves the cursor a given amount in the X and Y directions. And change icon, which causes the cursor icon to be switched. The display operation is not defined formally. Informally, it causes the icon associated with the cursor to be displayed so that the top left corner of the icon represents the cursor's position. When displayed, the clear parts of the cursor bitmap should not obscure the underlying objects. But this is just the informal part. So we have the methods supported by this cursor. The first one is create, which takes a quad and a bitmap and it gives you a cursor. The second is translate, which takes three arguments, cursor, integer and integer, and it gives you a cursor back. Basically, as we mentioned earlier, it moves the cursor a given amount in the X and Y direction and change icon, which causes the cursor icon to be switched. Then we have the position, which returns the current coordinate of the cursor. So we have the cursor and it returns the coordinate for that cursor. The change icon, we have cursor and bitmap, and cursor gives us a cursor back. And display, we have this cursor which gives us the cursor back. So these are the functions or operations supported by this sort cursor. So with this cursor, what we do is आपने देखा कि basically एक बहुत simple सा cursor का operation हम define कर रहे हैं, and the main thing is that this cursor is associated with the coordinate, and that coordinate is the one that we have just specified. So we are going to use that specification with that definition to define this new sort, which is our cursor sort. So let us look at the axioms very quickly. Once again, nothing very complicated about it, but that just shows you how things can be used to build incrementally more complex specifications. So here is our slide once again. So we have this translate create C, comma icon, comma xt, comma yd. So xt and yd, these are the displacements, is equal to create quad dot create xc plus xt, comma yc plus yd, comma icon. So this is what we do. So we are just taking the old coordinates, adding the displacement, and then creating a new coordinate and using this and associating with the icon. Then we have this position, create C, comma icon, is equal to C. That is the coordinate of that cursor that we have. We have position translate C comma XD comma YD is equal to quad dot create X of C plus XD comma Y of C plus YD. And then finally we have change icon, which gives us create C comma icon 2 is equal to create C comma icon 2. So we are now associating this coordinate with the new icon. यहाँ पर बस इस स्पेसिफिकेशन में एक चीज़ गौर तलब है और उस पर आपको थोड़ी सी तवज्जो देने की ज़रूरत है. रेस्ट इज़ वेरी सिंपल. अगर आपको इसको देखें तो कोई इसमें ऐसी चीज़ नहीं है जिसको ज़्यादा डिटेल में एक्सप्लेन करने की ज़रूरत होगी. यहाँ पर हमने क्रिएट का एक मेथड है जो इस कर्सर को क्रिएट करने के लिए यूज़ हो रहा है. And then we have a create method to create a coordinate. अब which particular create are we going to use? और जब हम create लिखते हैं तो किस create को हम यूज करना चाहते हैं. तो ये अगर हमने coordinate वाले को यूज करना है, so what we do is we say create dot coordinate. That is, हम ये कह रहे हैं कि ये coordinate की definition जो हमने दी थी उसका जो create का method था वो हम यहां पर यूज कर रहे हैं. So in this particular case what we are doing is we are applying a method that has been defined and specified somewhere else. We are not just importing this specification, but we are calling a method from that specification to specify our own methods. So ये एक पहली चीज है. इसमें इनहेरिटेंस वगैरह का कोई कॉन्सेप्ट नहीं है. वी आर नॉट इनहेरिटिंग बट वी आर यूजिंग इट. एंड हाउ डू वी यूज? वी आर यूजिंग द मेथड दैट हैज बीन डिफाइंड समवेयर एल्स. उसको इंपोर्ट किया और उसका मेथड हम यहां पर कॉल कर रहे हैं टू बिल्ड आवर ओन मेथड्स, टू स्पेसिफाई आवर ओन मेथड्स, जस्ट लाइक यू वुड डू इन योर प्रोग्राम्स. तो ये बड़ी सिंपल सी इसमें बात है. यहां पर हम इनहेरिटेंस का जो कॉन्सेप्ट है वो आगे चल के देखेंगे, लेकिन जो पहली चीज थी, हाउ कैन वी बिल्ड मोर कॉम्प्लेक्स स्पेसिफिकेशंस बाय यूजिंग ऑलरेडी डिफाइंड स्पेसिफिकेशंस. बड़ी सिंपल सी ये एग्जांपल थी दैट डेमोन्स्ट्रेट्स दिस पर्टिकुलर कॉन्सेप्ट. अगले लेक्चर में इंशाल्लाह आई विल कंटिन्यू दिस डिस्कशन एंड शो यू हाउ टू सॉर्ट ऑफ इनहेरिट और डू समथिंग सिमिलर एंड देन बिल्ड दिस स्पेसिफिकेशंस. हमारी स्पेसिफिकेशन आज जो कुछ हमने गुफ्तगू की उसमें हमने जो ख़ास तौर पे चीज़ें देखी वो दो चीज़ें थी. एक ये थी कि इन मैनी केसेस हम स्पेसिफिकेशंस जो हैं जब हम लिखते हैं तो इट इज़ नॉट ईजी टू राइट दैट स्पेसिफिकेशन इन टर्म्स ऑफ जो हमने वो रूल्स ऑफ थम्स वगैरह जिस तरीके से हमने जिक्र किया था. सो कॉम्प्लिकेशन हमें हो जाती है और हम मेथड्स हमारे पास कुछ ऐसे होते हैं. अगर मैं वो जो ख़ास तौर पे वो जो बाइनरी सर्च ट्री का था, अगर आपने देखा कि अल्टीमेटली हमने सारे के सारे हमने लिखे इन टर्म्स ऑफ क्रिएट या जो ऑक्सिलरी मेथड जो हमने दिया था बिल्ड का. अगर वो बिल्ड का मेथड ना होता तो हर जगह पे हम फंस जाते हैं. अगर आप इसको ट्राई करके देखें, आप इसको लिखना चाहें तो यू विल सी दैट. So in many cases, when you are stuck, you have to write the auxiliary methods and then write your specifications. So that is perfectly all right. The second thing that we saw in today's lecture was the special thing. That was if we have a specification which has already been written, how can we use that specification to build more complex specifications by using the method specified in that particular specification. इंशाल्लाह अगले लेक्चर में इस गुफ्तगू को हम जारी रखेंगे. उस वक्त तक के लिए आप मुझे इजाज़त दीजिए. खुदा हाफिज़ और अस्सलाम वालेकुम.